We can do 4 circles crystallography. This is a 4 circle, and in this case we have the cryostat for helium, liquid helium. You remember what I was telling you about the shelling? Because neutrons penetrate very well matter, we can put a good shell here, as much as a helium cryostat, liquid helium cryostat. But we can use a dilution refrigerator as well and make experiments below 1 Kelvin. This is what we get, diffraction peaks. Very much like if you go to the old times in X-ray crystallography. Now you don't see it because you push the button and you get a paper with the crystallographic structure finished. But in the old times you had to do all this with a 4-cycle diffractometer. So you scan in a given direction and get a peak. This peak, you identify it with a Bragg reflection, and you collect Bragg reflections, and you have to integrate the peak to know how many, which is the intensity, real intensity on all the neutrons you collected there, and then you go and go and go with your model and try to find a crystallographic model fitting your data. Very much like in the old times in crystallography. And here, what do you have? This, now, for you is very clear, these are like magnetization curves. But this is the intensity of the magnetic peaks. So very much related to the magnetization. And we can find the relation. Then you can get into the magnetic structure, and this is more complex, but you have to, there's no computer telling you, you push the button and get a paper, no one. With a magnetic structure, less than that. Okay. But you make the whole analysis, and you arrive to the configuration of moments that fit with your data. And I will skip that, this is very important. You can also, with polarized neutrons, you can determine the spin density. The spin density. This is very, very, very important. Let me go quick. Here you see the spin density distribution. In this problem, we were very, very concerned because the magnetic magnetic ordering was at a very high temperature compared with other compounds. So in that family, things were about 10 times higher in temperature. Why? Because the distance between iron and iron were very large. So we were suspicious that the things were more complex than look like. And in fact, when we did this polarized neutron analysis, we found that the ligands, like here, the chlorine, contain magnetic moment, transfer from the magnetic ion. So some moment was transferred to the chlorine, and then the interaction was not that far away. This was slightly magnetic. So help us to explain. The same with organic magnets. This case, for example, how it orders, why it orders ferromagnetically or like a canted antiferromagnetic. We went to the spin determination. We found that only here in this 5-member ring was magnetic moment. Nothing was here. Then forget to pack this molecule head to tile. Because if you pack this molecule head to tile, the tile here down is not going to do anything magnetically. We need to pack this head to head somehow. And we found that the diamond alignment gives the best, strongest magnetic interaction. This is how to produce neutrons in a nuclear reactor or by spallation. This is a high flux reactor in the ILL. And just to finish, this is more about the different sources, neutron sources. In Japan, you have fantastic neutron sources. And this is the ILL here. This is the reactor. This is the valley where the ILL is. It's a river. This is the synchrotron ring, the European spallation, European synchrotron. I always say ESRF. European Synchrotron Ring Facility. And this is the Institut Lauer-Langevin here. Beautiful area. If you like skiing, you can do a lot of work measuring, collecting measurements and so on, and one day enjoy skiing in the Alps. I went to LEL many, many times with my skiers. And I was working day and night and couldn't find the time to go skiing. Because what I was getting was more exciting than skiing. So thank you very much. Thank you for your passion. Thank you for giving me 15 minutes more. And I hope you got something from my lecture.